going to start the recording.
All right, I'm
Okay.
gonna let them, fellas, why don't you just kind of come over my shoulder real quickly? You'll all just introduce yourselves by name, and then I'll switch over to share the screen, and then I'm gonna get out of the way and not be a part of this anymore.
Okay. Um,
Uh,
uh, can you also tell me what grade you're in? Or you're on the same grade?
no, no.
So tell me what grade you're in too. Okay, go for it.
I'm Michael Reed, and I'm 11th grade. Just speak louder. Yeah.
Yeah.
11th grade, and my name's Michael Reed.
Hi, Michael.
I'm Justin Moss, and I'm also 11th grade.
Awesome.
I'm Jordan Pollock, and I'm in 9th grade.
I'm Noah Ryan, I'm in 11th grade.
I'm Smith Bashista, and I'm in 10th grade.
I'm Lucas Correa, and I'm in 11th grade.
I'm Nick Sophie, and I'm in 10th grade.
I'm Masud Waja, and I'm in 12th grade. I'm David Super, I'm senior.
Wow, I love it. 9th through 12th. You couldn't ask for anything better that you're all working together on the same type of project. So,
Right, so
awesome.
I'm gonna go ahead and just share the screen for the boys, and then I don't want you to hear me anymore.
Okay, no problem.
All right. Can you confirm site?
Yes, I see it.
All right, awesome. Canva's kind of glitchy.
Oh, here's Glenn. Hi, Glenn.
Just in time.
Just in time. They're starting. They introduced themselves.
Okay.
Excellent.
Right.
Go ahead. Let's start.
All right, go for it. Whoever's leading off,
So
lead off.
this is our slide deck. I don't really think we should say all the names again, but
Yeah.
this is all. And with a half hour is class mission movie, so
Louder.
louder.
Yep.
Yes. Louder, please.
Oh, we're
You're in Zoom right now.
Now we're in.
there we go.
Yep, you're good.
Yeah, we need slide two. Yeah, so let's see this slide. That's slide one. Oh, what's this?
It's like backlogging all your clicks, unfortunately.
Oh. Okay, so I see a robot. I see that you've got one, two, three. Looks like a total of 6 springs. Is that right?
What's that?
Sorry, Glenn. This is our network is being a little jumpy, and their slide deck is jumping along with it.
Hey.
All right, Justin or whoever.
So originally, we were looking forward to doing all 4 of the criteria to become the robot, but right now all the groups have just focused on figuring out how to store potential energy for the robot. But we're going to do this and better focus on one thing. Get it good.
So you're fading in and out.
Yeah.
When you talk, get right by the computer.
Yeah, just come up closer to the computer.
Yeah, get out of your seat and come up closer to the computer
Oh,
if you
there.
can.
Try that. That looks good.
So when we initially started researching, we tried to figure out how to get it to land. So some landing mechanisms for multiple legs below the machine to stop till you let it reach the ground. And ways to store potential energy were initially rubber bands, but then we thought that we should use springs because they're stable.
Mm-hmm.
Very good. Keep going.
So this was our original prototype. It was pretty much just a push-down mechanism that we would pull down from the orange rubber band. In this picture, it broke, but it's also old, so it's. But essentially, it was just supposed to get. There. Yeah. Can you guys see this?
No, after you finish your slideshow, we could
No, we can pin that.
see it.
Pretty much, it was just supposed to push down, and then it would hop off the table just a little bit because we didn't really know how it would work in practicality because we've never, experienced this before. But it was just nice to see it like jumping, I guess, a little bit.
That was smart. That was smart. Make it out of cardboard.
Okay. Now I've pinned your pay so I can see you guys better. Why don't you hold up the one that you've got right there?
Can they see it? I can't see it. Can you see
Oh,
it?
I see that. There's your first prototype.
Yeah.
Okay, very good.
And then
But then you have, oh, go ahead.
no, go ahead.
Well, I was going to say, you've got that blue one in front of you there. Was that your next step there?
No. This is like one of our subgroups designs because we have a lot
Sure.
of we have a ton of subgroups just to
Okay.
design.
No, keep going. I shouldn't interrupt you. Go ahead.
Thank you. Our main constraints, pretty much, our main ones were our inexperience and our time, but the time mainly came because we didn't have the CAD skills in the beginning, and then as we drew those CAD skills, it took us a while to understand like how it would actually work in real life and like putting it on because we've never done that before, and also just feel in general, but also just our resources. Like you'll see in this one, you'll see it soon. The springs aren't exactly like perfect. It's just we don't have the full resources, but we have like most of them, I guess. I'm gonna say.
Sure.
Oh yeah. Also, our class like is an intro class, so we don't have experience in other things outside of CAD, even just building, just just in general. But so it took us a while to get there.
So this is another subgroup prototype. This one's made out of metal. It's different from the other 4 that we have right now currently. And we're currently trying to make it out of a PLA material instead of the metal because currently a main factor is that the weight of the robot is too heavy. So it can't jump high enough just yet, but we're still working on that. So thoughts for new designs are we need to use lighter materials so it could possibly jump higher, which falls onto number 2. We need to be able to jump using different angles. So, like, he's basically trying to say so it could jump off a rocky surface or an uneven surface, like on a moon or Mars, anything that we need to. And then for number 4, the robot jumping needs to be automated so that you can't always push on the robot in the end design. So we're still trying to work on that.
So this was another design that we had. I focused more on using our laser machine that we have in the school. And as you can see on the left, I sketched it out just so we had some sort of idea what we were making. And it's basically I took inspiration from like the construction scissor lifts. And on the right, that was my first prototype of this type of design. I realized that I had too many degrees of freedom. Every red circle was a degree of freedom, and just flip that over to the other side. So I think there were 12 total degrees of freedom. So I took into account and I watched a bunch of videos and I looked more into the subject. So I resulted in using some type of spur gear that was made out of the wood that we lasered, and they would attach so each arm can't move freely, so they would be connected. So if one side moves, the other side would have to move. And then they were attached with a drive shaft on the bottom with collars to keep them so one side of it can't go one way and the other side can't shift the other way. With a lot of testing, I've found that like the wood's not the best for right now, especially when you're using compression. So we're gonna swap, and I'll talk about that later. But with the gears, they're just breaking after a lot of different type of springs I was testing. So if I go on to the next slide.
Michael, can you hold that up?
Yeah.
So maybe you guys can show them pictures of it, and then you can put a little like row of them in front of the camera when we stop sharing.
Yeah.
And then you could demonstrate each of the iterations and kind of how they work.
So,
That'd be good.
you can see that I spaced them out on the side, and I used hot glue because I didn't have anything else available at that time, but I just connected everything. It's just another view. Wants to load. For new designs, as I mentioned, I need better material, so we're gonna look at acrylic and laser cutting acrylic, and we're gonna see if we can. And we were discussing originally reorienting it automatically if it falls over, or making it maybe jump from both sides. It needs to jump higher and repeat the jump without failure. And we need to automate it, continue to task, and add camera. So add a camera. So it keeps falling over. So I was going to add a rod in the middle. We just didn't have time. But I guess I'll show them jumping at the end.
Yep.
Thanks.
So on the left, you can see was our first design, which was pretty much this. We were going to try and make it, I guess, more standard and more made out of, I guess, better materials to make it actually jump higher. But then we realized maybe it wasn't going to be as efficient enough, I guess. So then we moved on to our second run, which is a lot more complicated. But
For our second design, we looked at many different slip gear mechanisms to help with our load resources, because the motors that we have weren't good enough or strong enough to free spin and stop, and we weren't experienced enough to code the motor. For our first prototype, which one was the one on the left, we took inspiration from a piston design, and we decided to combine it with a slip gear mechanism so that we're able to retract and reload the spring in its position. But when we were testing it, we realized that the springs that we have were too high tension, and that the mechanism was too bulky and too complicated, leading to many points of failure, and ways where it could be potentially destroyed if one part was like malfunction. So we put it onto a second design, which we haven't been able to prototype yet, which basically does the same thing, but it's less parts.
You could use the cursor if you want to show them the specific elements.
Those wave springs look like they might be pretty pricey. What do you guys think?
yeah,
So our main problems with our first prototype was making it reload and fire without us having to do anything. For our first PDR, we just wanted to make it easy to go, so we didn't really focus on it. But we were still thinking of how could we mechanize this later in the future, as well as how many times we'll be able to use our prototype, make it jump, and how long would it last, as well as how simple it is and how easy it is to repair. Because when we use it, we want to make sure that we're able to fix it easily and be able to use the same model without having to bring in a new one every time.
Thanks.
So this is our robot. The design of this one is very similar to our original prototype. The thought process for it really was to just like keep it simple, just so we could, compute our time constraints. And the way it works is we compress downwards like this, and then the springs hold all the energy and it gets released. So originally we had two different designs, as you can see up there on the slideshow, one with 2 legs and one with 4 legs. In the end, we eventually ended up with, 4-legged design due to the fact that it had more stability, and also we had more structural support, so we could mount more springs to it instead of just having 2 legs with a very high tension spring. This helped like distribute that load off more legs so they wouldn't snap or break. So some pros of this design are that it is stable, more stable compared to the 2-legged design. It really helps keep like the center of mass. Another pro is the just simplicity element. You can see on the original one, it's like almost like exactly the same shape with all that stuff on it, and more structural support. Obviously, they have some cons to it. Most of them focusing around our material constraint. So for these legs that move, for the pins and joints, we have screws, and those cause a lot of friction, and the whole robot in general has some friction problems. So as a solution to that, we proposed using some sort of lubricant like grease or WD-40 around these. Another con of this design is the springs. We were working with what we had, and it just doesn't really. These springs are not like strong enough. They get stretched out after a few uses, so we're gonna have to look for something more permanent. And another thing is we have unswept edges that on the design. And those, although we don't have problems with it now, it'd be really good to sweep those so we'd have more support, especially once we move on to higher tension springs and the robot's going to be facing more force and more weight when we implement stuff like the cameras and all of the other parts we need to get it to jump at an angle and all that other stuff.
So on CAD, I designed a lot of the joints and combining all the pieces so they would be able to function and be assembled properly.
I designed the base and also the top. So the top is supposed to be a mounting part for the camera when we have it in the future, and the bottom has its area. So if we want to put a motor in the future, so it could be autonomized, that's an option.
So we made joints that bend to a specific diameter to make a circle that launched the robot upwards. And we made sure that every single piece was able to be screwed in and put together to make it as structurally sound as possible.
I think given the lagginess of the slide deck and the time constraint for the presentation, why don't we give you guys the floor just to show them the prototypes, how they move, and then we can pause for comment.
Yeah.
All right, so why don't you go one at a time? Start, all right?
You want to start with this? This was the original prototype as you saw.
Yep.
It doesn't.
Okay.
You got one. We'll do an order.
Oh, and there's your one out of metal.
Yeah.
Okay.
Well,
Okay. It jumps.
Yeah.
Sure.
This is the laser one. It's a little wonky because of the gears, but it jumps.
nope.
It is. Okay. Very nice. That's terrific. Okay.
Ours actually doesn't jump because we didn't take into account the split factor, which you can't even push down to get the energy.
Okay. So on this particular one, you've got springs that are a little bit too stiff. So you need some compression springs that to demonstrate that one. Is that right?
Yeah.
Okay. Where are you guys going for your springs?
for us specifically, it was just what he had in the garage, to be honest, because his orders aren't big enough for our for this design specifically.
Okay. And all I'm when I go to the hardware store, if I go into like the Ace hardware store, there's like 10 people that are trying to help me. And if I say, "Hey, I'm looking for springs," they'll take me over to this bin and it's got 20 different drawers and each drawer has like 20 different springs in it. And while you're there, you can go like this and say, "Oh, that one's too weak." Right? And you can go to another one and say, "Ah, that one's too strong." And you can go through and find a very specific spring for you, whether you want to use compression, tension springs, or torsion springs or whatever. They've got a very large selection. So that might help out with trying to choose the right spring for you. Okay. Now go back to the one with the four legs.
So instead, next time we're gonna put the springs on the sides, so it reduces the factorability of these
Okay.
talking with each other.
So you'll have 4 springs going between each of those. Is that right?
Legs.
Okay. And I think that's a good idea. Another thought I had for you, you mentioned how there was a friction problem. Um, I like what you guys have done. Here you're using screws, and you can imagine that the threads of the screws might bind up into the plastic a little bit. And so you might look to see if you can get screws that aren't all thread. Have you guys looked at that as well?
Yeah, we looked at that. At the moment, especially in the makerspace, they didn't have any of those. But for our next iteration, we're planning on using screws that don't have these types of threads.
Sounds great. And you might be able to switch to pins and then hold them on either side a little bit different. And exactly how to do that, I'd have to explore it. It sounds like you guys are already on a great path. I like your idea of going from the sides as opposed to going through the middle. Have you started looking at your motors for how you're going to do the compression?
Yeah, so we're planning on having a string that goes in the middle down, and we'll have a motor at the bottom, and it will just wind it up, and we'll have battery packs stored inside of the legs.
Oh, that's
And
neat.
also the wiring too stored inside the legs. The board will be on the top, same with the camera. We'll create a mechanism that stores both of them, and that's what we're trying to go at right now. And we're
I
trying
think
to
that's great. Have you thought about trying to put the camera down low? And what I mean is, if it's up high, then you have some of your structure in the way, but you seem to have a section in the middle where you could put the camera
yes,
and still be able to run it.
around here.
Yeah,
So like when you're saying when it jumps, it would have to take it from.
that's right. And it's not a requirement. These are just thoughts for you. I really like your designs. I like how you've gone through a lot of different things. I think it's looking really good. Let's see. Um, Also, well, one, I think it's kind of cool that there's a resemblance to the Star Wars AT-AT bike. I don't know if you guys noticed that. I think it looks kind of cool. Um, let's see. Oh, what kind of electronics are you looking at?
An Arduino board to control the motor.
Okay. And have you already found a camera that fits the way you want?
At the moment, no. But I do have a few options of maybe putting a GoPro on the top because I do have one currently. So maybe I could create a mechanism that could hold the GoPro camera.
And GoPros are a good option, but of course the difficulty is that there's a lot of extra material there that may give you some extra weight. If you look carefully, I think you might be able to find a camera that goes with the Arduino that you're looking for. And if you go to SparkFun, SparkFun has a lot of the code on that you will need for whatever type of camera you use to go with that Arduino. Does that make sense?
Yeah.
That way you don't have to write it all.
All right.
Okay.
All right, boys. Sorry, Glenn. I have to unfortunately send them off to the next.
Okay.
And I could listen to you guys dissect theirs all day and all the great information you give them. But I know we have a couple of folks in queue waiting for their turn, and I think their math and other teachers are probably waiting for them. Thank you guys so much this morning for your time.
Thank you.
Thank you.
Thank you guys. Great job. I love where you're going with this. Thank you. Okay. Have a great afternoon. Let's see. Next up is Glenelle.
Hello.
Good morning. Good morning.
Good morning. Yeah. Okay.
And I'm recording this. Is that okay?
That's okay. Yeah.
Awesome. Thank you for waiting. We're a little late.
No problem.
It's coming in.
Okay.
It's here.
Excellent.
Do you want to slideshow or you?
Yeah, I can change it.
Okay.
Can you change the slide? Yeah. Oh. I'm Kean Durenick.
I'm Andy Rice.
And I'm Maury Stone. We represent Glenelg High School for the Lunar Jumping Robot, Energy Storage, and Robot Body. And our teacher is Mr. Raymond Gershner.
For future space exploration, it has been deemed that the moon, more specifically the south pole of the moon, should be further explored. This is for two reasons. One, in permanently shadow regions of the moon, or PSRs, ice regolith has been found, which can be used by scientists and astronauts to form water on the moon. In addition to this, with the sun always being on the horizon, the south pole of the moon provides valuable landscape to put solar panels and solar arrays to generate power for other machines on the moon. One issue with this is the fact that the south pole of the moon has over 10,000 kilometers squared of area to search where the best place to put your machines. In the past, for other planetary exploration like Mars, NASA has used rovers like Perseverance or drones like the Ingenuity drones to mark out POIs on Mars of where they further want to explore. On the moon, it is very rocky terrain and there's no atmosphere, which means neither of these two methods work. With temperatures as low as negative
just
3.
A reminder that there is no morning ARL.
Sorry.
Again, there is no morning ARL. Any ARL students can come to the cafeteria for periods 1 and 2. Afternoon ARL leaves at 12:05 or immediately following a lunch. Again, 12:05 following a lunch for PM ARL departure.
With temperatures getting as low as negative 330 degrees Fahrenheit, it is also unsafe for astronauts to explore it by themselves. So for this project, we are going to exploit the moon's lower gravity and jump around the moon as our means of transportation.
So in order to justify this problem, we sent a survey out to our community and we researched asking basic survey questions about the South Pole of the moon. Of 155 people, 72% believe that exploring the moon will have benefits for further space exploration. 69% believe that the benefits to having people permanently stationed on the moon, and 87% believe that there's benefits to finding water on the moon. This just goes to show that the average human believes that there's benefits to exploring the South Pole of the moon.
We looked at many past designs to draw inspiration on, including the LEAP jumping robot that was designed to explore many of the plateaus on the moon, the space hopper that was built for microgravity environments on asteroids. We really liked Space Hopper's idea of using its appendages to change its center of gravity to manipulate its trajectory in midair. We also looked at the lunar injecting robot from last year's HUNCH that took pictures of a landing site on the moon. And we finally looked at Boston Dynamics Sandfleet, which drives around and used arms to position itself and then jump, and also drives around. And we took heavy inspiration for this in our later ideas.
Some of our more notable criteria and constraints we had for this robot is, first off, we wanted to have adjustable trajectory. So not necessarily like the force of the spring. However, it would be nice to be able to launch at many different angles in case of situations arise on the moon that you needed to jump in a specific angle. In addition to this, we also wanted to be able to take multiple rounds. It needs to last the whole workday of an astronaut without intervention. And it's important for it to be able to survive many different falls. Our goal is for it to hit around 10 feet at a maximum distance. For safety, we aim for 10 feet, but if you don't want to go any higher than that, and the weight we have envisioned for this is it's less than 2 pounds.
So here are two of many concepts. On the left, we have a driving robot with a spring and plunger. And then on the right, there is a quadrupedal robot with four separate actuators on its legs. The quadrupedal robot was decided was a little too heavy, and the driving robot didn't seem very plausible for our manufacturing abilities.
For our other designs, we took heavy inspiration from the sand flea. We liked the design a lot, especially the fact that it could rear back on its legs and provide a place for the solar array to get maximum sunlight on the south pole of the moon. The wheels could also make for good shock absorption on impact. And we also like the fact that it is very compact. But the only downside of this, it was heavyweight. So when we were looking into this design, we decided to make a latch energy storage mechanism for it, which uses a latch and linkage mechanism to store the spring energy until it is fully compressed and then release it all at once so we can get the maximum energy of the spring.
An alternate energy storage method we came up with was a winch. This winch would be released with a one-way clutch with a one-way bearing to separate the motor and the winch releasing. However, we ended up going with the latch for further designs.
Up on screen now is the decision matrix that we use to rank all of our designs. And some of the more notable ones you guys can see there are in a light blue. So our top two ranking scores were the Boston Sand Flea with the wheels and then the ones without the wheels. And it was deemed through the decision matrix that we believe that with the wheels, it would have been better. However, what you'll go on to see is that we actually decided to remove the wheels anyway, because it just added a lot of extra weight. And then down in the bottom is our final design after we got to our first prototype that we ranked in the decision matrix.
Here's our first mock-up that we made out of cardboard. It was mainly to gauge the size and overall design. We really liked the form factor. However, there were some pinch points between the wheels and arms, and there were a lot of sharp corners that we tried to refine in later iterations.
So this is our first CAD, and this is of the mock-up. It is approximately 5 to 8 inches, which we deemed relatively big. There are the wheels on there, but there's no internal motors for them. We decided to leave them out for right now just because of the weight. We also decided to make our spring latch design in CAD, which is driven by a brushed motor featured here. And we go on to explain the latch mechanism in further detail in the next slide. So our latch mechanism comprised of a screw and washer, which pushes the spring when the screw is rotated. So because the washer is threaded, when the screw rotates, the washer moves up into the spring, compressing it against the latch guards. Then once it's fully compressed, the washer will then run into these little bars, which then inversely moves these tiny pins in the design outward, releasing the spring.
And here's our second mock-up, which I have in front of us. It was a more refined version of our previous iteration with more smooth corners, and it was 3D printed. We really did like the way it sat and the arms themselves, and that's why we continue to go forward with the lifting arms.
One thing you'll notice about our CAD version 2 is this is where we decided to remove the wheels. We noticed from other podcasts that the weight was a main concern for this robot. Making this as light as possible is one of our biggest goals. So we decided to remove the wheels and motors to drive them. We also switched from our past design to 2 servos driving the arms instead of just 1, so we wouldn't have to run into the issue of gears or an extra rod to drive both. Then we also made it a little bit smaller. This one's 4.3 by 7 inches, just to keep the weight down.
We used many calculations, including the conservation of energy and projectile motion, to model the trajectory of our robot in flight. Because we have an adjustable angle, we found it very important to figure out how our robot would move at various angles. So we used variables in Desmos graphing calculator to graph many trajectories. We then used the spreadsheet software to see how different variables would impact the amount of energy and maximum force of the spring. And we then used Hooke's law to find an appropriate spring that would launch our robot 10 feet into the air.
We wanted to run at least 2 different tests for this robot, looking at different variables. The first one, we were planning on setting up 2 separate mats, a distance from each other, and using an external video recording. We would be able to jump the robot between the 2 maps and test the consistency of our trajectory. Obviously, the 2 maps would be separated different distances depending on what our calculated trajectory is versus the actual trajectory we got with the robot. In addition to this, we also wanted to run a test of jumping the robot straight up and down on a rocky surface. We would still use the movie mats for this, but we would put rocks on the surface and some dust to represent lunar dust. And the robot would be jumping up and down to take photos of the ground so that we could test the camera quality midair and see the prevention our systems have at blocking the lunar dust from getting into the robot.
So for our next test for this project, we're still trying to reduce weight. We're currently around 1.2 pounds right now, but we're trying to look at different materials to to minimize the weight needed. Ultim is a good 3D printable thing, but we don't have the manufacturing capabilities to do so. So we were looking at aluminum carbon fiber as our other main option. Both are heavy, but if we do a combination design where we skelletize the aluminum and then wrap it in carbon fiber, we can make the best of both worlds.
Do you guys have anything printed out that you can show us?
No, other than this mock-up. We do not.
Okay, well, let's see it. Stop sharing and let us see that one real quick.
So this was the model it was mainly to gauge the size, but it does have lifting arms.
No, I think that looks great. I had one, you were talking about trying to lose some weight and use some aluminum. Have you thought about using some aluminum cans?
No, we have not thought about that.
And part of what I'm thinking is that you might be able, instead of having a 3D printed skin, you might be able to use like a framework and then wrap some aluminum can around it. Just a thought for you. I'm not sure how that'll work, but it gives you some structural strength with pretty little weight. I like your legs that you've got. Can you show me how do you expect that those are going to work to right it in the direction you want?
With the arms?
Yeah, show me how those arms work.
So our idea is that once it lands, it will land hopefully back on the spring for a little bit of compression and then fall down. And then the arms will push the robot up. Or if the robot lands upside down, the arms will be able to right the robot, ready for the jump again.
And part of what I was thinking is that if you have them turn opposite directions, what does that do?
It would turn the robot.
It would just turn it. Okay, yeah, I see that. Okay, no, I think you guys have a great idea there. How big of a bottom pusher plate are you expecting to use?
About 1.5 inches in diameter.
Okay. Do you want it rectangular? Is it going to be rounded? How do you guys picture that pusher foot to look?
Rounded.
Okay. Okay. And why did you choose that?
So that it could conform to the spring. It could be rectangular, but the current design we have is circular.
Okay. No, I think that's really cool. And where are you going for your springs? Have you guys already found a spring or not?
Yes, we have researched spring on lines based on our calculations, and we found what spring factor we need, spring constant we need, what length we need, what compression we need, and we have found the spring on, I believe it's Century Springs. They are a spring manufacturer that does custom and stock springs.
Okay, and one suggestion I have for you is to go over to the hardware store and see if you can find a similar one and just kind of play with it a little bit to see if that's really what you want. It's one thing to do a calculation, but like in your drawings, I see that you are compressing the spring all the way down, and sometimes that may not be a requirement or even possible for that type of spring. But I like where you're going with this. I think it's really cool. Also, I see that you've got kind of a rectangular shape for the box. Is that how did you decide to make it rectangular as opposed to kind of egg shaped or something like that?
We picked the rectangular design so that it would be easier to write itself. So it would either land on one of the sides. So it would be like, it only has 4 possibilities of landing, of like a edge it can land on. Yeah, and for simplicity.
It also gave us a lot of internal area to work with when we were placing our components, so we didn't have to be as strict with our placement.
I think those are good reasons. I mean, and I bring up an egg just because you're going to have some mass that'll allow it to rotate a little bit once it lands. And I didn't know if that might be a factor that could be helpful. However, your boards and things like that would obviously fit better inside of something that was a little bit more rectangular. So I like your ideas, guys. I think that you're going on a really good path. Keep this up.
Thank you.
Great
Anybody?
presentation. I appreciate all your work on that, and it looks like it could write itself, and it as simple as possible. And I like the round corners too. So thank you for doing all that.
Thank you.
Thank you.
So you guys have a wonderful afternoon there. We have another Glenelg team.
Yep, they're right there.
Awesome. Thank you. Have a great day.
You too. How's it going?
Good. How are you doing?
We're good.
Good. Good morning.
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 So introduce yourselves. And I know you were listening, so that's good.
So I'm Andrew Schuster.
I'm Prisha Shah,
And I'm Dylan Fertilis.
and we're seniors at Glenelg High School.
Awesome. Thank you.
Should I just share the presentation?
I think he has it up. Yeah. It's up. Are we sharing?
Yes. Let us know when you're ready.
We're ready. Thank you.
Hi, we are Team Leap with Glenelg High School and our teacher, Mr. Gershner. I'm Andrew Schuster,
I'm Prisha Shah.
And I'm Dylan Fertilis.
and we are the Jumping Robot Project Power Systems and Controls for NASA HUNCH.
Let's begin with the problem. The south pole of the moon is home to essential resources such as ice, ammonia, and carbon dioxide, all of which are collected into cold trap volatiles. These resources are located in craters and pits 6 kilometers deep, known as permanently shadowed regions. Surrounded by rough terrain and steep inclines, it has become extremely difficult for previous driving rovers to navigate and map the landscape. Furthermore, the lack of atmosphere has eliminated the potential use of drones for imaging. Thus, the development of a jumping robot with imaging capabilities is necessary, as it will be able to effectively navigate the obstacle-filled area. The images produced by the robot will aid in future long-term missions by identifying the locations of the cold trap volatiles, which can then be purified and altered to develop drinking water, rocket fuel, and even breathable air for astronauts.
Before we officially started designing our own robot, we researched several prior solutions and patents, all of which were designed to either jump or image the lunar surface. The first of which was NASA Viper. The Viper rover was designed to image the south pole of the moon and is equipped with flashlights, cameras, and solar panels to self-sustain during its mission. However, it was never officially tested and never designed to jump. The jumping robot patent you see on the right uses one actuator for more efficient jumping motion. We plan to use as few actuators as possible in order to increase efficiency of our own robot and lower the weight. The Pragyan rover was also designed to image the lunar surface. Its completely vertical solar panel was a unique feature that we decided we may want to use ourselves when making our own design. However, Pragyan had a lot of issues with the extreme temperatures found on the moon and had a complete lockup of all systems. So looking at this, we can determine that we need a strong insulator to protect our own components. Intuitive Machines Athena was a lunar lander designed to conduct experiments on the lunar surface and was equipped with communication capabilities that we plan to either mimic or adapt to be able to communicate with the astronaut that will be accompanying our robot on the moon. Athena also tipped and prematurely ended the mission. So looking at this, we can determine that we also need some sort of self-righting mechanism in case our own robot tips and suffers the same issue. The last two robots we researched were the Grace Hopper, which accompanied Athena on her mission, and JAXA's Slim Lev 1. Both of these are jumping robots that were designed to image the lunar surface, and both of them have a lot of features that we plan to take inspiration from.
Grace had 144-degree cameras on it in order to take pictures, and that allowed them to have a very wide range and just capture more lunar surface per jump. And the Slim Lev 1 robot has a very large solar panel that covers a lot of its surface, so we plan to take inspiration from that.
After looking at the currently existing solutions, we began to develop our own preliminary ideas. For the control systems, we have 3 sketches here. On the left, we have the Pi Pico only, which had no Bluetooth ability to communicate with an iPhone. However, it had the ability to communicate with numerous sensors that we plan to incorporate into our design. In the center, we have the ESP32 and Pi 02W, both of which have Bluetooth and sensor capabilities. However, it would be extremely heavy and boxy. On the right, we have our automatic and manual system flowchart idea, where we provide the user with the option to go on the automatic route, which would basically function the robot until the battery's completely out of power, or provide the manual option, allowing the astronaut to reset the robot before each jump to take specific location images. Then we went on to develop our solar panel preliminary sketches. On the left, we have our expandable panels, which would basically come out of the robot, fold out, charge, and then fold back in once the charging was done. In the center, we have our single side angled panels, which would be calculated to a specific angle and be sent to a preset location on the South Pole to maximize the amount of power being absorbed and produced at a time. And then on the right, we have our body embedded solar panels, which would be on all 4 sides of the robot's body, and so that 3 sides at one time were at least getting sunlight. This would maximize the power and would allow for the body of the robot to act as a protective layer to the solar panels.
Now, once we had our problem, we came up with some specifications and parameters for our design. First, we looked at performance, where this robot must be able to average 1 jump every 8 hours over the total mission of the 10,000 square kilometers on the moon. However, we know that we're also going to be facing environmental impacts such as the sun and the temperature. And with the sun, we have very limited solar energy that we need to use to its maximum capacity, as can be seen with the calculations seen on the right, to be able to power the robot efficiently.
After developing our design specifications, we began to weight our different ideas based on them. We weighted functionality to be the highest, as the success of our robot would be determined by if it could actually function. And the highest weighted system we had was the Pi Pico and Pi Zero, which was less boxy than the ESP32 and Pi Zero, but was still able to have Bluetooth capabilities. Then for the power systems, the highest weighted was the solar panel and single type battery design. However, to the left, you can see that the solar panels plus adaptive dual battery system was just 0.5 points below in weighting. This was because of the heavy weighting of the actual system compared to the single battery.
Now, when we started our development, we started with a preliminary schematic of how we were going to connect the rest of our components to our charging module, except this design didn't really have any of the fundamental electrical engineering principles that we began to incorporate in our mockup, where we also incorporated a microcontroller. However, in this design, the solar panel was far too big, and we determined that this was not the right configuration, which leads us into our version 3, the detailed schematic. As you can see on the left side, we have 6 solar cells in parallel in order to increase the current without increasing the voltage, leading to an IP5306, which is a replacement from the TP4056 we were using in earlier models. This is so that we can have a consistent 5-volt output without having an extra component and extra weight add to the system. In addition, it's good to note that in this design, everything is the correct wiring and pinouts for the UART connection, sensors and actuators for everything, and it can be a good reference for our final design.
Once we had developed our schematic, we began looking at actual real-world components that we could use in our design. On the right here, we have our parts list, which incorporates our Pi Zero, Pico, our charging module, battery, solar panel, and a variety of sensors that we plan to incorporate into the robot. The total weight of this entire system is 0.356 pounds on Earth using currently existing numbers on the web. And we plan to incorporate 16 square inches of solar panel with 4 on each side so that a minimum of 12 square inches are receiving sunlight at a time. This would allow for, with the 12 square inches, have 16.2 hours to charge 1 battery. And if we plan to use 2, it would be 32.4 hours. The current total cost estimate of our entire system is $98.97.
And then we began creating our prototype, which is sitting here in front of us, but as you can see, we have a Raspberry Pi 4 and an Arduino Mega replacing the Pi Zero and Pi Pico that we'd be using in our final design, as this is what we had around the school. And there's a button on the board that activates the Raspberry Pi 4 to send a signal to the Arduino asking if it's safe to jump, indicated by the state LED seen on the bottom, which is determined by the temperature and coulomb count, determined by the potentiometer seen in the middle. Now, if it is safe to jump and the Raspberry Pi sends a signal it's ready to jump, the flashlight will turn on and a picture will be taken. Next, it's key to note that there's an accelerometer and a servo motor, where the servo motor counteracts the action seen by the accelerometer and gyroscope in order to represent the self-actuating capabilities we're going to have in our final design.
Once the design is fully built and functional, we will run 6 sets of tests in order to determine if it meets the criteria we previously set for it. The first set of tests will be to record the jump distance and the time between jumps to see how long it takes to prepare for one jump. The second set of tests will be looking at image transmission and seeing how long it takes the image to transmit to the phone and the image quality once it has been received on the phone. The third set of tests will be power use and generation. We will see how long it takes to charge one battery to full capacity, and we will see how many jumps we can use that one fully charged battery for. And the last 3 sets of tests will be to test against the damage caused by regolith or fine powder, extreme temperatures, and the impact from jumps.
These are our sources. Thank you so much. Any questions?
Yeah. So you say you've got something in front of you there?
Yes.
Something that you've, let's take a look at that. Stop sharing.
Hold on, let me stop. All right.
Yeah,
Let's plug that in.
Okay, so you guys have solar panels, you have your controls.
So in this, we don't have solar panels or the charging module. This is just the control side of things.
Excellent. That's just great. Okay, and you're doing it all off of just a 9-volt battery?
Yes.
Wow, okay. Very nice. Okay, so have you been able to get things to, do you have any plan for how you're going to get the jump?
Yeah, so basically what we plan to do is we plan to incorporate all the motors that the previous team is going to use in their design, and then we're going to power them to the needed capabilities based on their own calculations. And then once our system completely works, we will integrate it with the full body. Hold on, let me turn it back up so you're not staring at the mock-up. We will integrate it. We will integrate our entire circuit system and solar panels into their actual body. And then we will test for the full jump. But once we know the motor's working, we know our system is enough. And if the jump itself doesn't work, we can check to see if we need to send more power to each motor.
Excellent. Okay, and so you're working with, you're part of that robot as a team. Is that correct?
So we're kind of like that. However, our system itself is completely independent. We have just manipulated it so that it can meet the criteria of their robot for it to function. However, our system itself can function independently from theirs.
Excellent. And that sounds good. Okay. And so, okay, right now I see you've got a pretty big breadboard, and I realize that's probably not what you're planning for. What were you thinking about to move to from there?
So from here, we were looking at using a PCB board, and then also we're going to have the smaller microcontroller and microprocessor, and it's going to be connected with the PCB board. It'll be connected to the buttons and the different sensors, which we're thinking about wiring to the different ends of the robot based on where we need it. For example, the gyroscope is going to be on the far end of the robot because it'll be more accurate for self-actuating. And yeah.
Sounds good. Now, you also mentioned you've got an accelerometer on there. What kind of G-force can it handle?
So we are actually not sure about this current accelerometer because this is just one we're used for testing to see if it's self-righting. But in our final one, we plan to incorporate one that can function better on the moon. However, it's more expensive, so we don't want to prototype with one.
Sure, and that's fine. Part of what I'm thinking about is that, like that one that there was a video of, they mentioned that they were getting like 300 Gs, right?
Yes.
Which is a lot. Now, you're looking for your accelerometer to just look for 1/6 G so that you can tell what its orientation is. But of course, when it jumps, it's going to have a much higher G-force. And so you might explore and find out, is that an issue? Does that make sense?
Yes. It's essential we do the calculations to figure out.
Sure. And it'll probably if you look it up, it probably says in the stats for it what it can handle or not. Okay. Terrific. I like where you're going with this. And right now it looks like you've got a Pi 4. Is that right?
Right now it is a Pi 4, and this is the camera module. Planning on using camera module 3.
Show me that.
Yes.
Show me your camera module.
Here, you want to hold it, and then I'll bring it up to the actual camera.
Yeah, and that one looks really small. I think that's a great idea. And I noticed that you've got a very long cable on it as well. I think that's also smart because it allows for you to place it in a lot of different locations on the robot. I think that's terrific. Excellent job, team.
Thank you.
And I see that you've got some indicator lights. What are those for?
So we do have a state LED at the bottom here, and one wire just got disconnected, I think.
Sure.
We have a state LED at the bottom here, and as the temperature or column count gets to more hazardous levels, I'm not sure if you can see, that's yellow for light hazard, and then it's red for like extreme hazard, and this will prevent the robot from actually jumping. However, if these values are within safe ranges,
What's important?
if these values are within safe ranges, then
the flashlight should turn on and the camera should take a picture. And in our
That sounds great.
It's displayed on a serial monitor, which we haven't incorporated here because we work on it separately, not here. And it's displayed on the serial monitor to basically represent what a phone would show.
Okay. And so now when it's not safe to jump, is it going to rotate your motor? Is that right? To be able to reposition it?
Yeah, so the ability for it to be safe to jump is determined by the temperature and the charge of the battery more than the actuation of the robot. That is part of it. If it does sense motion and it's still actuating, it also will not let it jump. However, it is more determined by the temperature and external factors.
Okay, very good.
You can see, I'm pretty sure the wire's all connected now. Maybe not, sorry.
That's okay.
But we have the blue LED. Essentially, the Raspberry Pi is sending a UART signal to the Arduino that is telling it it's ready to jump, and it's communicating through UART to communicate back and forth its condition and everything.
That's really cool. What do you guys think your next step is?
Probably our first next step is to finalize an insulator choice because of the extreme temperatures we will face. Right now, we're thinking we may want to use Kapton, which is commonly used in spacesuits and electronics to like insulate them. It's an extremely strong insulator and can survive temperatures from negative 269 degrees Celsius to 400 degrees Celsius. So it's extremely strong, very thin, lightweight. So I think it'd be a great choice to insulate all of our components to make sure they do not freeze up.
And so while he's doing that, we plan to also develop an app that will communicate with the robot itself to let the astronaut know of its charge, and it will send the images to said app. And this can help with the actual function and allow the astronaut to know to take the robot back inside that it's no longer functioning and to prevent any additional damage. And what do you plan to do then? And so we're also going to finalize our circuit. And once the circuit itself works, then we will take it and we will actually implement it into a PCB board. And then we can actually begin our testing.
Excellent. Excellent. I think you guys are on a great path. This looks really good, team.
Thank you.
Really nice presentation. Thank you so much. And you can always send us questions. So,
you bet.
I also like the way you're thinking about all the different safeties and the way all the systems interlock and work together.
Oh, that was Mike Bennett. Hi, Mike.
Thank you so much.
Thank you for joining. All right. Have a wonderful afternoon. And that was the only two teams from Glenell, right? So we are going to move on to Tri-County. And you can stay on, Glenell, if you want.
All right, we're just
thank you. Okay, thank you. So Tri-County Regional Vocational Technical High School, you are up. And I see you're starting to share your screen and you've done it. Thank you for waiting. I know we're a little late.
Hello. Hello. So we're the students that are working on the lunar jumping robot here at Tri-County Regional Vocational Technical High School. And our teacher is Mrs. Magus. My name is Nolan.
My name's Angel. My name's Owen.
My name is Matthew.
My name's Aiden.
And my name is Jack.
And Owen will be starting us off on the presentation today.
The most important part about jumping is the energy. We can't really jump if we don't have any energy because there's nothing to move. So the first three concepts that we made were the thrusters, the motors, and the springs. The first one that was out of the picture was the thrusters. Way too expensive, way too bulky, and way too complicated for us to understand. The second one was the motors. They didn't store enough power to launch the motor, the robot into the air, but like Salter's robot does, which is does not have any springs and it's just the motor launching it 3 feet up in the air. We believe that the springs are the most viable option to launching the robot up in the air.
All right, so some of the springs that we decided upon are compression springs, extension springs, and torsion springs. We found compression springs were exceedingly difficult to work with because of how much force they exert, but if we can use them, they will be very beneficial to our robot.
Extension springs are very reliable to use. They're very useful in all sorts of things, but do have some notable downsides. But in those downsides, the torsion springs make up for that. So I believe that the best robot design will have all of these springs combined into one initial design, and that will jump the highest. Some prototypes we made were the bear trap, the one on the bottom right. So the bear trap was a two-legged thing barely, where it had a spring attached and it would snap close. That's why we named it bear trap. It would launch up 3 feet up in the high in the sky, and it was very dangerous but very powerful. So we couldn't really go with that. Next one that we made was the frog legs, which is on the top middle. It jumped pretty high. It uses rubber bands, which is in replacement for torsion springs, and since rubber bands do not work in space, so it replicates the torsion springs instead of actually using torsion springs. It uses tension. The next one that we made was very similar to the frog legs. It was a three-legged frog. It had another leg which increased stability and but did not allow it to jump any much higher. We learned that no matter how many legs that you have, if they are the same power, it will jump the same height. Next one that we have is the cannon. In the middle of all the images is the cannon. It's very heavy, very powerful, but not powerful enough to reach across to reach flight. So it wouldn't do really anything. It was too heavy for any of us, and that's really it. The next one was the second most successful, and it was the syringe. It would jump up in the air using a tension spring and fall back to the ground, and maybe landing on its own thing to repurpose the energy back to the next jump. But it wasn't very reliable.
All right, so some of the release mechanisms that we have investigated so far are a winch with a ratcheting gear, a gear rack and a slip gear, and a cam, along with a disengaging motor, which will work with the winch and ratcheting gear along with the gear rack and slip gear. These all store the potential energy of the springs and turn into kinetic energy, allowing the robots to jump. And some controls that we will need are the to detect if we're orienting or detect if we're on the ground and we need to orient along with jumping.
And in terms of our body materials, I have looked into different types of aluminum alloys, and I found out that they're like easy to get and obtain. They have great durability and are decently lightweight, like especially compared to other metals, but have a very large range of expansion and shrinking based on extreme temperatures, which can be a problem. And then if I have plans to explore other types of metals, including different types of stainless steel or titanium.
So at the beginning, we were looking at the different stability and orientation sort of things. So we were originally looking at reaction wheels. We did some testing with them, but after the testing, we kind of concluded that to make viable reaction wheels that would be small enough to fit on there while also not using the frankly absurd amount of power normal ones do, it would just be too hard for us to develop because we just don't have the time, or really we just really just don't understand the full concepts of them. So that was put off off the thing, and we kind of looked to more of a passive stability instead of active. So it just like allow it to passively try to orient itself in a way.
Also, I have tested different types of weight distributions and shapes in order to put it into the design for passive stability, and then I plan to go into more designs with that in mind.
One suggestion given by the creator of Salto, Justin, was that to make a cage around the robot so it can just survive landing and not just land on its feet again. So it just would reorientate itself on the ground instead of just reorientating on the air.
So when we were looking for different camera systems that we were going to use, we looked at mainly three sort of things, which was kind of Arduinos, Raspberry Pis, and ESP32 cameras. We kind of got rid of Arduinos right off the bat because they don't really have a very good camera system, and they're kind of big and bulky. Even the smallest Raspberry Pis, smallest Arduinos, don't really have a good camera system. The next thing we kind of looked at was the Raspberry Pis, like the Raspberry Pi 5 and the Raspberry Pi Zero. The Raspberry Pi 5 is good because it has multiple camera ports. The problem is it's significantly heavier than the rest of the other things and draws a little bit more power than the rest of them, which it makes up for the power and the computing power, but it's just bigger, bulkier. So we decided to start looking into ESP32 cameras, which for the size comparison, they're significantly smaller while still having a decent amount of computing power, which allows it to actually what we've done was we've taken the pre-made web server software that you can get off the thing, and we've made it so that it actually, instead of connecting to a Wi-Fi of someone else, it makes its own Wi-Fi network and then uses that Wi-Fi network to make its own web server. So any device that connects to that Wi-Fi network, from a phone to a desktop, can log on to that IP and look at the camera from pretty decent range when we have the antennas connected. This example of it working, we have it connected actually to a battery, which is then connected to a voltage multiplier, which goes into the camera. And on the left, you'll see this is just an example of also the different settings, because you can have different resolutions, different quality, brightness, contrast, whatever you might need for different things, all on a phone thing. And you can start streaming, and also you can start streaming so you get a live video. You can also get still images in in the thing that we're doing right now is we're trying to incorporate different things. Like we have an MPU 6050 accelerometer and gyroscope so that it can measure its velocity. Once it gets to a specific velocity, it actually sets it so that once it reaches that velocity and it keeps going up, once it reaches 0 at apogee, it will take a single picture from all the cameras, and then it will come back down, land. You can reset it up and do that all over again. But just for weight, ease of use, and versatility, we decided to go for the ESP32 cams.
For the battery type, we decided on lithium polymer batteries. And we also used a solar charger and boost converter to get a 3.7-volt battery to get it to a 5-volt. And we use solar panels to power the robot's battery. And we're going to have separate systems for jumping and motors as well as cameras.
So as I was talking about the MPU 6050s and accelerometer gyroscopes, that's what we're going to be using for testing right now. We don't know if that will be our final one, but I want to use that idea so that it's able to take a picture without any like us going in and having to take a still picture. I also want to adjust it to code because on that website, it only shows one of the 4 or however many cameras we want to do. So I want to see if I can use the cameras and they can communicate together to try to get all the different outputs on one page. So you're able to see all the different outputs on one page, and we're able to get pictures easier than the things. Also about the pictures, they're going to be stored on 2 places. Hopefully we can get them to take stills on the whatever device you are on. Also, we want to be able to also take pictures and store them on SD cards on the actual cameras themselves, because each one of the cameras has a micro SD card slot. So I want to do that, but that's basically what I want to do for camera controls.
The next steps that we have for the bodies is that I want to go more in depth into trying new designs and new types of strings in like corresponding with each other. So like extension springs next to expansion springs or torsion springs. I want a design that incorporates all of them so it all gets all the benefits from all of them while also circumventing all the downsides from all of them. I also want to go into more biological anatomy since a lot of the animals that jump do it really well and they have much more time to get rid of all the flaws, and it would be really amazing just to base stuff off the animals.
What I would like to do, I would personally like to develop a prototype of different release mechanisms so that we have a universal mechanism that would work with any of our different designs so that we can jump whenever we like to. I'd also like to integrate different motors and controls into our jumping so that we are able to move around and get through.
Yeah, and quickly, sorry for saying this again, but with the next steps with the multiple camera connections through one site and the camera arming like the arming of the acceleration camera picture thing.
And what I would like to do is develop a way to power the motors of the jumping to incorporate it into the controls as well.
And then in terms of the shell of the body, like I said earlier, further looking into and testing different shapes and weight distributions for a body, and then looking into different metals and for a body as well.
Thank you.
Thank you.
Do you guys have any questions?
Yeah, I like where you guys are going. There's some really great ideas in here. Can you stop sharing? Let's take a. Do you guys have some of your prototypes there?
Yes, we do. So we got the 3 frog legs,
Wow, look at that. That's cool.
It would jump by, sorry about this. We don't really have that much space.
No, I understand. Okay, and I saw the video, so that was cool. And you mentioned about weight. Um, Now, with what you've got there, I mean, so Legos are like ABS plastic, and going with another material could save you a lot of weight. But also the rubber bands are terrific. But of course they may not have as much strength as what you might get out of a spring, right?
Yeah.
Okay. Excellent. I like that one. That's a really cool idea. Now you said that the other one you had that was just like two legs. Is that right?
Yeah, that other one is now this one.
Oh, okay.
Since
No,
this
that's
one
really
is
cool.
this one is just better in every way. It increases stability since it has three legs and jumps more straight up.
Yeah. No, that's really cool. Okay. Show us the next one.
This is the one called the syringe, since it looks
Uh-huh.
kind of like a syringe. And you would just push down and it would just jump up.
And I think that one's really cool. Now you've got a lot of weight on that one just because you're using metal. Um, and also, what would happen if you put your spring right down the center of the or if you put your rod right down the center of your spring? Would that be possible?
It would just be incredibly difficult to do. It might mess with the friction. It might like connect with the rod, so increasing friction. So I just decided to put it on the edge, like on the side, so it wouldn't affect the thing. But it would have had more power.
Yeah, I think that it would get a little bit more consistency if you ran that rod straight up through the center, and then just reorienting your springs, I think will get you where you want to go with that. But I think there's some really cool ideas there. Excellent job.
So this one that was just way too heavy for anything.
And what would happen if you had switched out from metal to some other material? Do you think it would have jumped a lot higher?
We tried with Lego and elastic bands. It just kind of flipped.
Uh-huh.
I should probably delve more into it to see what's the problem. But right now, I'm not completely sure why it doesn't jump.
Oh, okay. Well, and I think that each one of these, I think all of them have good validity, and it's just a question of how are you going to arrange them and minimize the friction to be able to see which one works best for your design. So I like that you explored all of those different jumping methods. Good job, team. So which way do you want to go? Which kind of style do you want to aim at?
I'm not completely sure. I don't think that any of these will be a final design because I think we will make a much better version in general since
I
all of these
agree. I think that you can choose any of them. It's just which one do you think is going to work best for how you want to attack the problem.
So I'm thinking about maybe this not being any of these being the correct one, but using the information that we gathered from each one and making a better solution in general.
That sounds great. Do you have so where do you want to go next, guys?
I want to go more into instead of just using one type of spring, I want to try and using maybe two different types of springs, like extension and torsion or something like that. Maybe increase the force output on the.
Okay. And when you do that, that's going to mean you have to have a stronger motor and whatever as well to be able to compress it or tension it or whatever. So I think that is all very reasonable within what you've got. What kind of materials do you think you want to use for that body?
Lots of like different types of metals. I kind of like went into the as I said the aluminum alloys a lot, but I didn't like I didn't really go that much into like highlight my fare and like on the moon, but like there were a lot of drawbacks that like especially in I looked at aluminum alloy 7075, and like compared to like the other one I looked at 6061, like there was a lot more drawbacks compared, and like overall metals are really like heavy anyways, so
Well, consider your aluminums that you're looking at. Those are all great ideas for the final version, but of course you don't need to make that right now. And so your next prototype, you can start off using you know I see that you've got a cardboard body that you were looking at. There's no reason why you can't start off with something very lightweight like that. And if you switch from corrugated cardboard to like a cereal box kind of cardboard, you can also get a lot more variety of curvatures and things with that. And another thing that might be helpful with weight and sturdiness, imagine like how many times can you throw a plastic bottle up in the air and it land on the ground and it still works just fine, right? So look at some of those really lightweight materials that are already kind of structured, and you might be able to implement some of those into your design. Does that make sense?
Yeah. Thank you for that.
And so, let's see. Mike, you got any thoughts for him?
No, again, for prototyping and just proof of concept, I wouldn't worry too much about the weight, just to prove that the joints work the way they want to, the springs react, and then refine it from there. So cardboard models, like Glenn was saying, refine that, just proof of concept. If it works on that scale, then it'll work on a smaller scale and more refined. So I'd kind of start that way, I think.
Mm-hmm. Yeah. Thank you, guys. Well, and save all these 3 different iterations on display for your critical design review. Don't take them apart, in other words, unless you have to modify something.
Yeah. Excellent job, guys. Keep up with this. I think that you have several different designs that you can either combine or take from as you move forward. I think you're doing a great job, guys.
Yeah.
Thank you. Thank you very much.
Really good. And you can always ask us questions. We're here to answer questions. So thank you, Tri-County. And you all have a wonderful afternoon. So we are actually going to move into Billings Career Center. And they have 2 robot teams that work separately, but in the end, they're working together. And it was really fun to watch them because I get to go there. It was really fun to watch the 2 teams talk together and draw how they were going to cooperate. So Billings Career Center, you're up.
Hi,
hey guys.
I'm Asher Kennedy.
I'm Torrance Sminsky.
We're all we're sophomores and he's a junior at the Billings Career Center. We were on the body of the robot. Are we pulling up the slides?
Yeah, you ready?
Yep. So starting with the problem of the robot, which was addressed by you guys, so you already know that, but we have to have a robot that repeatedly jumps and crashes back to the ground, and it has to be able to survive those repeated lands on the ground. And our group really took the approach of surviving the impact back to the ground first before we moved into the inner brains and really constructing how it's going to operate. So our first thing that we printed was just a little, basically,
they can't see that.
Yeah, it's just a little tennis ball made out of TPU that we 3D printed. And the idea is that we have this exterior cage around the robot. We scaled it up. It's basically like a airless soccer ball. And the idea is all of our components will fit inside the cage. So when it launches, it'll come back to the ground and it'll absorb the impact. This is made out of TPU, so it's flexible. Torin has done the research on what kind of materials that will be used because TPU wouldn't work on it.
So one of my materials that I thought would be useful as the outer body would be polyether ether ketone, which is like a really durable resin that like can withstand like a lot of heat. And like for the inside body here, one of my ideas was just like regular aluminum because the inside body doesn't really need to withstand like crushing force like this. So it could just be like durable right here and just flexible out here so it can compress.
So then for our inner body, where we'll have to store all the brains, with the camera, the electronics, the motors, and all the servos that will operate the robot, we decided to house in a dodecahedron shape with all these arms that will connect. You can see this is like a little cutout of what the exterior cage would be like.
Yeah, you're on screen share. So you want me to turn off screen share so you can show these things?
Yeah.
Okay, I'm gonna stop share for a second.
So
and then you guys can go up and hold it up or bring it up here.
Yeah, that's what it's.
So this would be our inner body, the dodecahedron, and then we would have these tension points in between the outer shell. So this would be a piece of the outer shell, and then these are made out of flexible TPU. So it compresses in, but when it's pulled from the other side, it won't be stretched. And now we have mounting brackets. So this will all fit in within a scaled up version of this. And this is the nose cone that will hold the top all together. Okay, back to the slideshow. Yeah. I'm in developing the solution. Slide 3. All right. One of the batteries I found was called the Eneloop. It's like just like AA or AAA battery because I found that like a regular like brick battery would be way too heavy for the concept we're doing. And another thing I found was like a coating for the battery so it doesn't overheat. And like one of them I found was all right, one of them I think it probably would be like the same as the outer body, so polyether ether ketone, because it is really like one of the best like heat resistant materials out there. And that's about it for the batteries. That's the picture of the battery and some of my research. Next slide.
Yep.
The left side is our base concept. The bottom part is like sort of interchangeable. That's our the next team, but the top half is our base design.
So the idea is that you can see in that photo on the exterior of the cage, you can see there's these little arms, and that was a very, very rough prototype in a drawing that we came up with. And the idea is when the robot comes back to the ground, it'll probably land on the top of the robot because when it launches on the moon, there's going to be no fins to move the robot in the right direction, or even when it launches, if it's set in a certain direction. But the center of gravity will have to be towards the top of the robot, which will cause it to land on its nose. And so once it lands on its nose, which a few slides in the future, you see we have this nose cone, which will prevent it from stalling directly on. It's a few more than that. We didn't go over. There on the right side, you see in the top right picture, it's this little nose cone that would prevent the robot from stalling directly on its head when it comes back to the ground. Our arms that will be on the side will be able to fold out and reset the robot on the top, these are the arms right here. We need to figure out how to put all of these, you can see top right, there's that picture of the arms. And we need to figure out how to put this mechanism into the inner brains while the arms are on the exterior of the cage. And yeah, so on the left there, that's how this would probably all come together, with our arms on the exterior and that top drawing on the left photo would be the arms on the side, the brain on the insides, and then all of these little connections from the interior to the outside cage. Bring the next slide, Mr. Anderson. This is the inner body. The idea for that, we had a misprint where we accidentally put the pins on the inside. So once we fixed that and printed it again, we found that the dodecahedron came together really well. And I kind of held up the first prototype of the cage in that lower right photo. And that is possibly what it would look like to have the body inside the cage. And that would have all of the electronics in it that would run all of the arms on the side, which are in those photos. Yeah, so that's the a very, very rough prototype for the nose cone. Because the center of gravity will be towards the top, so it has a stable launch. That nose cone will prevent it from stalling directly on its head. So if it's sitting at an angle on the surface of the moon, the arms will have an easier job of resetting itself.
In the lowest left-hand corner, you can see the idea to re-level itself with the ring that would be on the bottom of it. And those blue arms in there hinge up and down. So it would, if it landed on its side, it would push against the ground to re-level itself.
I think we can go back to our camera.
You can go over our view. Our view. Turn off, Jared.
Yeah. So all of these, I think, because you couldn't see during the slideshow.
You might want to get up closer to that camera, or else bring it back to like.
Okay, I'm gonna bring it there.
Yeah, come up closer so we can see some more of that. Those are looking really interesting, guys.
They have a camera in the back.
There we go. Look at that.
Yeah, so the idea is that this dodecahedron will store all the inner components. We've done some research on that. Torin has all that information with the camera and battery and motors. But with this being the storehouse, there will be these connections that go to the exterior. That's that exterior. But we need all of that to also hold a bracket that will hold our arms. And these arms, if you're looking at it from a side view, these would be connected inside to a motor, which when it turns would move these arms down. It would reset itself onto the ground right there. And then it would be able to launch. The other group has the launching mechanism. And then because resistance in air and everything isn't really a problem with it, whether these are already back up in the robot or still down when it launches, we haven't really gone over that issue yet, but we aren't very concerned about it right now.
Okay, so hold on before you walk away with that. So I see how the strings are going to pull it in one direction, but if you use strings, how do you reset it to the original position?
Yeah, so we have a string here on, let's see, I'm moving the opposite direction. Yeah,
Good
so
morning,
we have a
Fairport.
string.
Who would like to see Mr. Shaw behind Mr. Clauser? Or
We have
maybe
a string
Miss
here on the
Olsen?
top, and
Clear
then a
out your
string
closets
here
because from
on
now
the
until
bottom.
December
And the
25th at
idea
noon,
is Isaac
we
is
will be
about to
hosting
bring
a
up
clothing
the
drive.
motor mechanism.
All new and used
But
clothes,
if this is
adult and
connected
children
to a
clothes
shaft
will be
spinning one way, and this is connected to
in
a
front
shaft
of
spinning the other
counseling
way,
again,
it
and
will
the
move
winner will
together.
be
So when this
tight.
pulls, this one stays
Candy
tight, and when
grams
this
are
one
here.
pulls, this one
Send a
stays
candy
tight.
cane of 30 animals
Okay, and that sounds good. Sounds like you've got a plan. Now, the next question I have, let's wait here.
It'll be on sale in the comments daily.
Sorry, I can't stop the announcement.
Understand.
Final reminder, cap and gown orders were due over break. Finally, thanks for all the free food. We collected over 1,400 pounds of food and the pantry is full. If you need support over the holidays, see Ms. Barron's in counseling. Go Career Center, go education, have a great week.
So this is a simple 3-pin switch design that I put together. So it just reverses the polarity of this little motor. And so what it would be is if we spin a rod and the rope is wrapped around the rod and they're equal distance, as one spins one way, it would make the other one unwind, and that would make this go up and down as it would need to, and then they would all work together at the same time.
And I think that looks great. Okay, now I see that you're using a lot of TPU, and I'm guessing some of this is ABS or PLA. Is that right?
Yes.
Okay, and so when you add all of that together, it starts looking a little bit heavy. Do you guys have plans for how you want to shrink down some of your designs so that they're not quite so heavy?
So originally we were going to make a upscaled model, and then once we get all the pieces where we want it when it's big, then we can all scale it down by an equal percent and make the whole thing smaller.
We figured that once we figure out a rough prototype, being able to figure out different materials and scaling it down and everything in that category will become a lot more clear once we figure out how it all comes together. Because as of right now, almost every different aspect of the body of the robot is a different part for us right now. So once we get a solid body, we can figure out what is unnecessary and what could be lighter.
And I think that sounds really smart. I think you're on a good path there. Just a couple of thoughts for you. You might look into seeing if you can swap out a couple of the parts so that instead of a 3D printed thing, you might be able to use like some rigid wires, right? Because they could they could just cut you back on some of that weight. And what I'm thinking about are like for example, when I went to the Renaissance Fair, they had these, it was like a head massager, and it was a group of wires, and you kind of push it on your head. Have you guys seen any of those?
Yes.
And what I was thinking is that those kind of wires, they've got a rigidity that would work similar to your legs, but they would have a lot less weight to them, and it might help you with that problem. Does that make sense?
Yeah.
Yes.
And even like the ring that you've got holding that, I think that you might be able to lighten that up as well with something similar. I like your design. I think it looks really exciting. Now, right now you're using the flexible TPU as your elastic material. Now that may not work so well on the moon. Do you have thoughts of how you want to change how you would do that for the flight unit?
I'm thinking for the outside, just like a resin or like a resin with like some metal rods in it that are flexible so it can add to the structural stability of it.
Yeah, Torin has found multiple materials we have in the journal that have listed the pros and cons to weight or the temperature and those constraints. He's found some resins that look pretty good for what we're looking for. Although we're not set on any one idea as of right now, because again, it's not one unit right now.
Sure. No, I think it's sounding good. I think that there are other options, some of which are metal, and some of which can be other types of plastics and things like that. So I think you have plenty of directions to explore there. Excellent, team. Where do you want to go next?
Our next steps after today, I think, is again this bracket that has held the arms. Like you said, it's very unnecessary as of right now. This was just to demonstrate how they'd operate. We'd like to make this bracket integrate with our body. So this bracket may not be a thing anymore, because there could be ways to fit it in directly into the body. We've also figured that having having 12 of these connection points may also be unnecessary. For when we get a camera, we're thinking that sticking a camera out of the body, when it launches with the center of gravity, right, it'll be horizontal to the moon when it's at its highest point if it's launching at an angle. So then the camera would be looking straight down at the moon.
Okay.
So taking away some of these connection points, making everything really fit together, and we also need to start looking into which cameras and also solar panels, which Torrin has done research on.
That sounds terrific. Now you've got that dodecahedron in the middle. What kind of thickness do you have on the sides of that?
Yeah, so the exterior of this shape is what is it? It's 0.2 inches. And we didn't really, our biggest thing with this was just getting the angles on each of these panels to be able to construct it. The thickness of it, I think it's probably exaggerated right now. We've printed it out of PETG carbon fiber. So it's a little tougher than other basic materials. But our idea is that our inner brains could be very, very, very light, just because our exterior cage will take all of the beating when we hit the ground. So this will store all the components, but it may be very light, and these outer walls could be a lot thinner than 0.2 inches, we're thinking.
Excellent. I bet you can. I think that you can probably save some weight on there. That'd be pretty significant. Excellent job, team. Any other thoughts or ideas there?
Questions?
Do you have any other questions for us?
No, but we do have Mike Bennett and Nancy Hall. They might have some comments or questions.
No, I came in on the middle of them. So, but I was able to see what it looked like and how they were thinking of writing itself. So from what I was able to see, it did look good. But yeah, other than that, don't have much.
Yeah. And that writing itself is very important. So don't lose that. And instead of string, use fish line, which is a lot stronger. And I know y'all go fishing. And so, yeah, no, it's a really good design. And we appreciate your work on that.
Yeah, thank you for your time.
Thank you so much. And now the second part of the jumping robot.
You just need 1 minute to switch out on the table here.
Yeah, I'm glad the first team is staying to listen. That's important. So thank you. All right, introduce yourselves, and then you can share your PowerPoint. And you don't have to go over the problem or the constraints, because we know that really well.
I'm sure you guys are already sick of that.
Yeah.
Excellent.
All right.
I can tell it's already a very different design.
Well,
this part they're doing how to make a jump, the energy.
Yeah, that's all right.
I'm Ryder. I'm Cole.
I'm Sarah.
This is our jumping robot. We did the controls and the power storage mechanism.
Okay, you guys ready to share screen?
Yeah.
And then we can skip the first two slides.
Yeah. So the first step was brainstorming. We looked at a lot of different things. I've got them all in this notebook right here, actually. So one of the first things we looked at was animals that jump. We had like frog, kangaroo, bunny, a bunch of different ones. And then we sort of realized that that was a bit of a dead end because that would be extremely hard to do compared to our other ideas. Do you want to jump? So our other ideas were hydraulics.
That won't work.
Yeah, that wouldn't work on the moon, we realized. Neither would like gas compression. So we
The electro stuff.
yeah, we looked at like polymers that would change shape when you apply electricity to them. Shape memory polymer. We realized that that was also too complicated to do. So we eventually decided on just springs and gears. Next slide. Once we decided on that, we got to work brainstorming ideas to get a device to jump with springs and gears. Our first idea was just a plain and simple spring that went straight down like that.
And we would use like a pulley system or something to reload the spring.
Yeah. We decided against that though, and we got to brainstorming again because we realized that that would also be just weird to do. Which brings us to
This right here is our current idea. It resembles a lot like a bow, or what is that called, like a bear trap?
Yeah, bear trap. How they work. Instead of using like springs and just springs, we used basically leaf springs, which is just a long piece of curved material that when you bend it, it snaps back. So this is our first prototype right here.
You want to go off of Jared?
Yeah. Here,
Stop sharing so we can see that better.
Yeah.
Oh, there we go. Okay, now show me.
You're gonna bring it to the back or?
This almost needs to go up.
Very good. Okay.
So this the green part right here is just the frame because we couldn't use their body design, so I just sort of like made a frame of what their body would sort of be like when we did this. There'd be a hole right here for a string to pull this back, and then it'd go like that. This in here right now is TPU, and we're kind of realizing that that doesn't work too well. This is one with a carbon fiber, and it has string on it. You can't see it very well.
No, I can see that. That's good.
Yeah, okay. So
okay, so you pull on it.
Yeah.
Very good. Okay.
So that's the basic concept of our idea. We're just trying to find a way to make it work right now.
And then if we can go back to the slides we have.
Okay. Now, just because it looks a little bit different on camera, what type of string did you use for that?
This is metal
So I
wire.
could grab one.
Uh-huh.
So it's 0.32.
And just a thought for you, you might use like a braided like a braided fishing line?
You're thinking using like more.
Does that make sense?
Yeah.
And what I'm thinking is a monofilament is okay, but sometimes I think that you can get the braided, the stranded stuff, and it'll be a little bit stronger, and it can handle the winding up onto a smaller spool if needed. Does that make sense?
Yeah.
Okay. I like where you're going with this. Where did you get your carbon fiber?
This is just carbon fiber filament we have here for the person.
Oh, it's carbon fiber filament. Okay. All right, keep going. I don't mean to slow you down.
You should go back to it. Yeah. So that's the base concept for what we have for how we're going to get it to jump right now. Could you go to slide 9? This is what we decided on for the controls.
We thought it would be easiest to use something that like is already connected to a remote controller. So we ordered an RC car that had a camera as well. And so we're gonna try and take apart those controls and use that.
I like that. That's really cool. Keep going.
Yeah. Could you go to slide 12? So this is what we had for the mechanism that would pull it back. There are flywheels at the top aligned with the holes on the here. I can actually go up here sort of and show you at the same time.
Can you guys see the video right now or just my screen?
I just see the screen.
Okay, never mind.
Here,
Okay. So these we put flywheels up here, and then there'd be gears that would connect to a motor that would pull it. Yeah. And then there'd be a split in the gear that would once it got to that point, it would let the flywheel release and it snap back.
Very good. Okay. Go back to your CAD drawing for me. Okay. Interesting. Okay. One thought I have for you is when you're pulling it up, right? You're in contact with the ground a very short time, even though they're in motion. Is there a way so that you get to have it to orient your leaf springs in a way that they would be in contact with the ground for a longer time so that more of that energy is transferred into the jump?
Like making feet on them?
Maybe. Yeah, that's actually not a bad comment right there. By putting feet at the bottom of it, right? And part of what I'm thinking is that if this is your leg and you've got if you stretch it back up like this, it's only going to be in contact for a slap. Whereas if you were to have like maybe a foot on it, like you suggested, it would be pushing the whole time that it's coming down. Does that make sense?
Yes.
And that might give you more of a jump for the amount of tension that you're putting into your component. I think you guys have a really cool design. I think there's something really, really interesting about it. Oh, wow. Now another thought for you. Right now you've got as you print out these, they're fairly I think that you could get more elasticity if you printed them a little bit thinner. What do you guys think?
The legs?
Yeah. Well, we've sort of run into a problem and we're still workshopping the construction of the legs right now because they're very thin and very delicate. We've had problems with snapping, so we're looking into different materials, different infills, and yes, different thicknesses and lengths.
So instead of 3D printing them, are you able to find some carbon fiber rods like that?
We could definitely try that, yeah.
And check that out, because when you're 3D printing it, you're not getting as much strength as if they're made all as one piece. Does that make sense?
Yeah, and Glenn, I was gonna say, if you look at like tents, a lot of tents comes with those carbon fiber rods because they're designed to bend and everything. So if you go to a store like that, and you could probably get some in different sizes too.
I think so too.
And even to add in on that, model shop, since you're already working with models, model shops will also have carbon fiber reinforcement rods, sometimes for airplane wings. They'll also have stranded cable fibers that are very, very tiny, be used in all different control systems. So even fishing rods, perhaps, on those, even a fishing rod.
Those are some great ideas. Huh, like tent poles or something like that. But those are like a fiberglass usually.
Right.
Huh. Great thinking, team. Holy smokes. Okay. And is that all of your slides, or did I interrupt you too early?
That is all of our slides.
Okay. Where now, in terms of that, tell me about that. What is this?
These are the TPU legs we tried. I didn't put enough infill on them, so they're not strong enough, but
way too big.
It's just one of the materials we looked at.
On that, you can even look at the print orientation as well as the infill. What type of printer are you using?
We're using Prusa MK4.
Okay, so I know that you can adjust, as you were talking about, you can adjust your infill to whatever degree, and they have different infill patterns too.
Yeah, we were looking at those as well.
Great.
No, those are some great ideas, team. I like what you're doing here. What do you think your next step is?
And now I think we'll look into putting feet on the legs and then going through different materials that we could use for the legs, just to get the bend and the what's it called, durability.
I think too, it's been a while since we've communicated with the other group, so we definitely need to get some more relationship with them.
Sure. I'll tell you, that is one of the toughest things about this about design program is communication. Just everybody staying on the same page as you do your progress. So I think you guys are on a really good path. I think there's something very interesting here. You know, I haven't seen a design exactly like yours, so I think you've got something pretty unique, and I like it. Good job, team.
Thank you.
A really nice presentation, and keep working on. I love the experimentation on what leg will work the best for your thing. But try to go to Ace or to a camping store and see what else you have. Even at home, you might have something. So thank you so much, and have a great rest of the morning. It's only 9:15 in Billings, and we have another Billings team that's going to come, not Billings, another Montana team in Bozeman, Montana. So thank you.
Okay.
And we'll
hey, Flo, I messed up the times on my kids, so I've got one of them here. He's gathering his stuff, but I thought it was 15 minutes later than it is. But we have two teams, so we have two slots, but they're working together.
Okay.
So I'm gonna get them going. I've got to get their presentation up, and then I'll have Mikhail start since he's here. He can start giving the presentation, and then as the other kids come in, they'll pick up where they need to.
Yeah.
So,
So,
Mikhail, you ready?
so this is Gallatin High School in Bozeman, Montana. They have two teams, one working on the body and one working on the propulsion system.
Oh, that's smart. I like that.
Yeah, and they're working basically together as kind of as one team, but two are kind of focusing on one area, two on the other.
I think that's really smart. Very good.
Yeah. Okay. So, Mikhail, why don't you go ahead and start, and then as the other kids come in, we'll get them set.
They see this thing.
Not yet. Go to Zoom. So go to there, and we got to go share screen.
Maybe?
No. Where is the share screen button? Why isn't that?
Run your cursor
There it is, right
down
there.
the bottom. Yeah.
Right there. And then you want to choose that window.
Okay.
Share. And then put it into slideshow.
Cool.
There you go.
All right, guys. Can you guys see it?
It's coming up. There you go. It's on.
We see.
All right, sweet. So, as you guys know, we're working on the lunar jumping robot. I'm Mikhail, and when my crew does come here, it'll be Evan, Simon, Sebastian. So
What?
wait for them.
Simon, come on. We're on now.
One of them.
Keep going.
So, the design summary we have was the goal was to create a robot that can jump on the lunar surface and do surveys, take pictures of the surrounding area so that the astronauts can use this for further missions. The jumping robot will operate in the south pole of the moon. The terrain will be rough with rocks strewn across the mountains and hilly landscape. Throughout this presentation, we had a lot of fails, mainly when it came to the skeleton for the spring. See that right there? Yeah. You guys see that?
Oh, wait. And what is that?
So this is supposed to make sure.
Oh, that's your spring.
Yeah. So this is spring holder.
Oh,
And
I see it. Yeah.
the one thing I forgot to do was put a hole for the string to go through.
Oh, okay.
So fix that. And I don't know, we're having lunch, so we had spaghetti.
That happens sometimes.
So then one of our friends, Ivan, made another mechanism where the spring will be held in here and it will compress and then expand more. However, as you can see, it's quite blocky and it's very cumbersome.
Okay.
So we moved back to the idea, finally got the hole in this time.
Okay.
And hold on. We actually put in the skeleton, and then we have this part.
Okay.
Where it'll sit on top. When it will wind up, it will compress and then shoot.
Very good. I like that idea. Kind of like some of the Nerf guns.
Yeah.
Very good. Keep going.
So, if we had room, I would show you how far it sprung up. However, Simon said we should double the spring.
Okay.
So we did that, and this thing almost hit the ceiling.
Okay.
So when you try to put it all together, it was very tough because there wasn't enough room to work with on here.
Okay.
So we made the legs bigger.
Okay. Now is that TPU?
Yes.
Yes, it's TPU.
Okay. Keep going. Excellent.
However, one of the next problems we had was trying to bolt this to the legs themselves. So
Are you still screen sharing?
Yeah, we are.
Why don't you jump out of screen sharing so they can see a little easier?
Yeah.
Yeah, and I
there.
pinned you,
Stop
so I pinned you so we can see you. Actually,
There you go. Is that better?
Yeah.
Yeah, that's great.
Yeah.
Sweet.
That way, when you're seeing it, it's easier to see.
So, what Sebastian did was build these little clamps to clamp the body onto the legs right there.
Okay.
However, it is very difficult to get the bolts in there.
Yeah.
So we have to figure that out, which we're getting to that.
Needle nose pliers, right?
Yeah,
Okay.
we use pliers, even still trying to get past the ones with the motor holder.
Yeah.
was difficult.
Okay.
I'll share my screen back. So Simon, you have a chance.
What have we shared?
It's just the fails of the legs and body.
Okay.
Okay, so I see on the right side you've got a motor inside your body. Is that right?
That's correct.
Okay. And so that's what's going to pull your string. Is that correct?
Yeah.
Okay, very good. Keep going.
So, how do I?
I just two arrows. Perhaps, maybe. Hold on. Okay.
Okay. For the body, we decided to use an octagon shape for better balance and more storage space. So this is the body design we chose. Our teammate Sebastian built that. And then for the legs, we decided to do this design because it seemed the simplest and the least like heavy. So we decided to go with that for the legs.
Okay.
So the legs, mostly just like a spring. We need to add like balancing legs. So can I see the body?
Yeah. It's a big one because it's easier to see.
So on this, there will be like legs coming out like this, so that when it tips over, they can like reorient it. There will be four on each or one on each leg to reorient the robot if it tips over, hopefully. And then right now, all of the electronics hopefully do fit. We still need to test putting all the wires um in the electronic area, and then we need to figure out a locking mechanism that'll release the string when it's ready to launch the robot.
That's basically what we've been doing. So
Yeah. For this is a work to be done slide. What we need to do is we need to build a camera mount on the body, and then build a top cover as well for the body, because right now we don't have any way to mount the top cover, or we don't have one built anyways. So we need to do that. And then the final thing we need to do for the body is build a release mechanism. So kind of how a pen would work, when you press it down, it locks the ballpoint part out. And then if you press it down again, it releases it back into the body. So that's kind of what we're trying to do, is where when the string's all bound up and the robot's compressed, then it'll kind of like click and then it'll just release. So we were hoping. We need to figure out how to design that. And then for the legs, we need to add a better spring. And then we watched a video on a robot sort of like this, and they had rubber bands to help compress the robot. We're gonna try that maybe. And then we need to add the reorienting legs, so that the robot can like reorient itself.
Very good. Okay. Stop sharing. Let's take a look at what you've got again.
So the closest we got, this is the prototype of how it's going to work. So the body would be all clamped up here. I would do it, but as you saw, it's very hard to put the clamps in the body on.
Sure.
So this string would be mounted to a motor, which will wind it up like that, and then we'll just let go, allowing it to jump further.
Okay.
However, when we did some tests, we only got 12 centimeters off the ground.
Okay. And I wouldn't worry about height as much as at the moment. Okay, so right now you want to put the motor up on the top. Is that correct?
Yeah, so the motor will be, as you saw in the picture, the motor will be planted into this area right here.
Show me some more of that orientation about how that all fits together.
Just hold it together. Yeah. So it's going to be like, so you can't see that. Yeah, it's like this.
Okay.
Not to the top.
And is that the orientation it's going to be when you get ready to launch it?
Yes.
All right. So when it launches, does the motor, the mount, and the body all jump together?
Yes.
Okay.
And so, um, now that looks difficult to position so that that weight is up top.
Yeah.
Is there something that's gonna make it so that it stays in that orientation for the jump?
Yes, so when it's like this, we need to redesign these, but we'll have legs out here,
Okay.
hopefully, or maybe like in between the two that will be able to, like when it tips over, we can like have the leg like pick it back up, kind of like that.
Sure.
Okay. Do you have a weight for that white box on top?
What was that again?
Do you have the weight for that white box on top? Because I'm like with Glenn, that seems like a lot. I know you want to make room, but it seems like right now that circuit board may be the one item that's the longest. So if the circuit board isn't that long, I think you may be able to shave some space off that.
Yeah.
Because that's my concern. All that weight is going to be a lot on it, and it's going to end up wanting to be top heavy if it tips over. I'm glad you guys have the legs because I think having that is good. But definitely look to see if you could shrink that box. What is the box made out of? Is it
This is PLA. That one's PLA. Yeah, that one's PLA. Yes, this is made of PLA.
okay? That's good. It's not that heavy. Yeah.
Yeah, and we actually made the legs bigger, so I should be more like this.
Oh, okay. Okay,
So
that looks. Yeah, the other one. Yeah.
yeah, because we figured out that double spring in the mechanism will make it have a way more
Okay.
jump to it.
Yeah, and just remember the requirements originally were for 10 feet, but now the minimum is 3 feet.
Yeah.
Glenn mentioned there's probably not a lot of classrooms or areas. So as long as you can get, the 3 feet. Glenn, did you see that their jumping thing is actually a lot bigger? That one looks that one looks better.
Yeah, compared to
Yes.
the original.
Yes.
No, and that makes sense. And so one thought I had was, would it be possible to put some of that body inside surrounding the spring?
Maybe I think so because
And
so we
what
have
I'm
a lot of
thinking is,
redesigning.
so you've got the ball, you've got your spring. Now put some of your electronics right in the middle, and then keep your motor up top, and be able to pull it down. That might give you some of that extra. It'll bring your mass down, and it might make it easier to make the jump. Does that make sense?
Yeah, that makes sense. Yeah.
I
can see
like where
that.
you guys are going with this. I think that's a really an interesting method of doing it. I hadn't considered it that way before. I also so you've got your spring, and then you've got the rod that's in the center of it. Make sure you lubricate that, because there's going to be a lot of friction of your spring as it goes up and down there, and that can help you get a little bit more jump out of that stored energy. Does that make sense?
Yeah, actually, it's kind of funny because every time we were testing it, it's made a very squeaky sound, and we're like, we probably should fix that. Yeah.
Well, and you might sand it as well. By
Yeah.
sanding it down, you're going to get rid of some of those ridges, and I think you can get a lot more jump out of that. Okay?
Yeah, so for this one, the original design for the skeleton was, we did make it way bigger, so we sanded it down more. But then where I put it? The updated one, I made it slimmer, so it's easier to put the spring around.
Yeah, yeah.
So
I think
yeah,
that's smart.
yeah. So yeah, definitely sand this down now that you say it. And we also think about elongating this so it can actually fit the two springs together into this piece.
I think that's very smart. I think you've got a great plan there. Now, are you using like a fishing string monofilament?
Yes.
You might look at getting a stranded fishing string, and I think you'll get a little bit more strength out of it, but it also allows it to be wound up on a tighter spool. and that can also help with making it uh, uh, just being able to fit into your enclosure the way you need to. Okay.
What was that suggestion called again? The string
It's
stuff?
like a stranded fishing line. If you go into one of the fishing shops, they'll be able to help you. Just say, "Hey, I'm looking for something stronger than a monofilament," and they'll say, "Oh yeah, try this." Okay. Very.
You may want to mention to them that you don't want it to stretch. That's the big thing.
Yes.
You want the monofilament will stretch when it gives with their fishing lines. That actually you've got to be careful because they don't stretch and they can actually cut you or something. So they're very strong. The other thing is, I mean, I'm sure y'all know this. WD-40 is not a lubricant, so it's more of a cleaner and the water displacement. So it's really not a lubricant.
Yeah. Using something like a Vaseline or a grease would probably be a little bit better.
Okay.
Got it.
All right. Good thoughts. Good comment, Mike. I didn't say that right. Any other thoughts, Flo?
No, I like the design, and I like that it will it's important to self-correct itself if it's off to the side, because we want it to launch, take a picture, come down, and launch again.
Got it.
Got it? Awesome. But the design is really cool. And you only have what's needed, right? So it should be as light as you can make it. That would be great. And so you're just half the team. There's another team going to present this morning?
No, they I don't know why they're not here. We have the schedule where I only see them every other day, and I didn't see them yesterday, and I sent them emails to remind them to show up, and made arrangements for them to get out of class with their teachers, but apparently they didn't follow through. But this is one of each side of the team. So Mikhail's on the legs, and Simon here's on the body. So I think you got a pretty good overview of the whole project.
Awesome.
So, I mean, it worked out. We got a little extra time if you guys have more questions for him, or otherwise, we'll help you keep on schedule.
No, we're actually now going to be ahead of schedule. So that's very unusual for us.
Yeah. I was hoping you were going to be behind because I got the time screwed up when I set this up. So
yeah, glad I came early.
Yeah.
But I'm making a recording of this so you can come and the other members can see the recording of it.
Perfect. Hey guys, how do you expect so you tighten it all up and then you release. How do you plan to do the release?
So, remember when I talked about the pen lock design?
Yes. So you want to have a mechanism like that?
Yeah. Hold on
I
one
think that's
second.
really smart.
Yeah, you have something, Simon?
Yeah.
Yeah.
So when you press the pen down, it locks right here.
Yeah.
But then you press it again, it comes out. So we're thinking doing something like that where it would lock at the top when it's fully compressed. Like it would lock here and then it'd release when you press something, or it just release when it's fully compressed.
And I think that's actually a really smart idea. Have you taken apart a pen and started modeling that up at all?
Yeah, I have a pen model from last year because it was one of the projects we did. So it's very helpful.
I think that's terrific. And I was going to suggest one, I like your idea. Another thing that I'd mentioned to some of the other teams is, like in a fishing rod, when you're reeling it in, you are engaging the gears, right? But then you flip over the baler and you can cast. Well, that's exactly the same kind of thing as what you're doing is, you've got a time when you've got to wind it up on the gear. And then when you want to cast, you are releasing so that it can spool out. And so there's a couple of ways to do that. I'm not a fisherman, but I like looking at some of their equipment. And you might even do a video. You might look for videos on how they do it. So I think your idea is perfectly fine. But of course, you get into something and it might turn a different direction. So just be aware of some other options. Okay. Good job, guys. I like what you're doing. Keep this up.
Awesome. And you can always send us questions, guys. I do have one more question. How are you thinking it to be autonomous or remote control? Because I remember last year you guys were making a robot and you wanted to make it remote control. And I said no. And then I felt bad about it. So were you making it?
What I've come up with in my head was that we just have a system, a code system that would just
Okay.
constantly loop. But there's be like pause this so the thing can orientate itself and make sure it's all ready before compressing, jumping. And I was thinking if we make it compress in midair, it'd have more of a base to land on. So it'll be easier to jump again.
Yeah,
So yeah.
and these guys haven't really been working on the control side of things.
Yeah.
Originally, we were going to try to work with Bozeman High and have them doing the electronics side, but it didn't work out. It was just too difficult to do between the two schools.
Yeah, that is.
So they've been kind of basically concentrating on that physical side of things and the physical design of the body and the physical design of the legs. And I don't think they've spent much time on the whole control
Oh,
system.
control system. That's okay.
I understand.
Yeah, that's cool. Because
All right.
you came up with a very unique design, which is
I
great.
like it.
Yeah.
Okay. Good deal. Do
All
we
right.
have another school to go to, Flo?
Frontier, which is next, and is Frontier on at all? I don't
Andrew
know. Oh,
Schuster.
George,
One minute,
Frontier to everyone. 1 minute. George will be on in 1 minute.
That
George
sounds good.
is Frontier.
Okay.
That sounds good, George. Thank you, Glenn Gallatin.
Okay.
Because Frontier wasn't really required to be here until a few more, not until 10 o'clock my time, 11 o'clock your time, 12 o'clock their time.
No, they're working it, so that's good.
My goodness.
We can't play Clash Royale.
Hi, Flo.